So our next topic and last one for today, which is actually shorter than the last one, so bear with me. You shall be released soon. Programming languages. We actually, when we talk about programming languages, we can talk about them in terms of their generations or their levels. So first generation or first level programming language, that would be what we call just machine code. That's just zeros and ones. Now, if we translate those machine code into something that sort of has some little bit of meaningfulness in it, then that would be our second level or layer computer language, and that would be assembler or assembly language. Then on top of that, we would, and it is on top of that, because what we find is the assembly language actually does a, I guess you could say, a conversion to get machine code, because the computer can only use machine code. So any other layer of language that we have to do is going to have to be translated into machine code. And we have, so we have to have a tool to do that. Now we might use an interpreter to translate it into machine language, or we might use a compiler, but we'll talk about that in a minute. So our first level is just straight up machine code. Second level, we're going to do a little translating into something that's a little bit more easier for people to use. So that would be assembly language or assembler. Third level, we call high level languages. High level languages, that was the purpose of high level languages, is to make them more usable by people. And so we had a scientific high level language, which is called Fortran. It developed in the 1950s. We talked about Dr. Grace Hopper. She invented the programming language called COBOL, which was a business friendly programming language. We talked about Ada Lovelace. There was actually a programming language named after her called Ada programming language. We talked about Blaise Pascal. There was a programming language named after him called Pascal. Then came C. Actually, I shouldn't say then, because C is kind of old. It would be as old as Pascal, not as old as Fortran or COBOL. But C programming language in the 1960s and 70s, and it's still with us. Very nice programming language, able to do a lot of things in C. And then we have some offshoots of C, C++, C#. So those C# and C++ actually moved into a higher level still. So we have our very high level programming languages, which include object-oriented programming. And so, for example, Python programming language that you guys are going to learn, that's a very high level programming language, very powerful, actually. And you look at it and say, oh, it seems like a basic language, right? So people can just pick it up and start programming. That was the idea, right? But it's able to do a lot of things. And a lot of what it's able to do is because it has very nice libraries, and you'll learn a lot about those. All right, so let's talk about this program here, which is actually a program for a person who's cooking things, so a recipe. And how does that relate to programming? Well, let's see. So a recipe, we've got some ingredients. I guess you could consider them to be like data. When you have a program, you usually have some data that goes with it. Okay, they could be the ingredients. And then we have some instructions, what you do with those ingredients. And the instructions are important in terms of what you do, but also when you do it, which thing you do first, which thing you do next. If you do it in the wrong order, it's going to not be right when you're cooking. Well, that's the same as when we're programming. So it does kind of relate to the way we do our cooking. So our recipe is like a program. A program is going to be a bunch of steps. They have to be done in the right order, and you have to have the right data to go with them at the right time. And so, you know, that's the analogy, and that's how that works. Okay, so let's go to the next slide. Can I do that? I think I just do this. Oh, yes. So slides 3 and 4. This is slide 3. The next slide is slide 4. They represent the same problem. Okay, so you're supposed to compare. This set of cartoons is the same problem as in slide 4. We'll look at slide 4 in a minute. But let's look at the cartoons. What we see is in cartoon frame number 1, we see a rock, and we have a sword that seems to be stuck in that rock, and we see somebody who's trying to pull that sword out. We also see, and maybe this is a clue to us if we ever found ourselves in the same situation, is that there's a lot of bones that look like human bones around the rock. To me, that would be like, oh, there's a warning. I don't know. Anyways, so dude pulls on the sword and trips. And when he trips, the sword goes up and impales him on the rock. And I'm guessing now that maybe that's what happened to all those bones. They did the same thing, right? All right, so that's expressed in pictures. Now we can say it in words. Once upon a time, a man found a sword stuck in a stone. He thought it could be like Excalibur. Hence, he tried very hard to pull the sword because I guess he wanted to be like the king or something, right? Eventually, he succeeded. However, sudden pullback was so strong and he tripped, and the rock behind him, falling on the rock, impaling himself. That was very sad. So the important point to look at there, as it says in the notes, and you do have these notes. These notes are on D2L, and you can look at them as you go. The story is presented in two different ways. It's the same story presented in two different ways. Now, when we do our algorithms, we use the same idea. We can present the same algorithm in more than one way. So an algorithm is going to be a step-by-step to solve a problem. Step-by-step can be represented in more than one way. So just like our story of the guy trying to get the sword out of the stone, we can represent our algorithms by pictures, and we call that a flow chart. And we can represent it by stories, which would be plain English, but we also have a structured way of writing stories. And actually, we used to use that term structured English, and we changed it to pseudo code. Pseudo meaning almost like, means similar to is pseudo. So pseudo code is similar to a program. Right? So it kind of looks like a computer program, but it's not. It's general purpose. So, I mean, if you write your pseudocode correctly, you should be able to translate that pseudocode into any programming language or to any programming language of this particular type. So more likely we would use it for a high-level programming language like C, Pascal, or Python. So in other words, what I mean by that is you could write your pseudocode and one person could say, oh, I'm a Python programmer. I'll program that in Python. Another person could say, oh, I'm a Java programmer. I'll program that in Java. And it would be okay. The same pseudocode could be used for two different programming languages. Get the idea? Or C, or Pascal, or BASIC. Okay, so the same story represented in more than one way. And we can do that in our algorithms in more than one way. We can use plain English, which is just to say things, right? Okay, so first you're going to do this, then you're going to do that, then you're going to do that. That would be plain English. It's not too rigorous. It's not very structured. And so because it's not very structured, it would add to some ambiguity, and ambiguity is the enemy of computing. Ambiguity means if you have a single idea, which could be understood in more than one way, all right, in multiple ways. That's ambiguous. We don't like ambiguous. Humans can do ambiguity. We're okay with that. You and me, we can do ambiguity. We do it all the time. Like you're at home and your mother says, "Would you cook me breakfast?" Boom, you'll go and do it, right? Say that to a computer. What? To a computer, you have to be really, really specific. You'd have to say, okay, move the robot to the sink, go to the fridge, get 2 eggs. And you have to even be more specific than that. Whereas with a human, you could just say, oh, just please make me breakfast. They would go to the fridge, they'd figure out something, you know what I mean? Get the idea. The keywords there are figure out, right? Or else they might look there and say, there's no food. Taliban. No. Now, I'll go and find some somewhere. You know what I mean? A human would solve the sort of the fact that we could understand this in many ways. A human would get that, but computers don't. All right, so we have plain English. I mentioned pseudocode. I sort of mentioned. I said that pseudocode is structured. So yeah, with pseudocode, we always do things in a certain way. We use a bit of indenting. Indenting means that anything that's indented is dependent on the thing that it's indented below. And we also need to have a start and an end. We got another nice way of doing things. I don't know, some people don't like it too much, but I think it's fine. It's been around with us for a long time, which is a flowchart. With flowcharts, we have special symbols, and special symbols have special shapes. The symbols I'm referring to are the shapes. By their shape, we know what they are. And so just immediately looking at a flowchart, seeing the symbols, we kind of know what's going on. With pseudocode, we put our little statements between a begin and an end, and the statements need to be written in a way that they're easy to understand. All right, so pseudocode, as I said, they have special symbols, which are shapes. So we got these shapes at the start and an end there. What they have is they have rounded edges. So start and end has rounded edge. Inputs, they have these rhombus shapes, which are these four-sided things that with the uneven angles. And then the rectangle represents a process. So input and outputs also are that shape. Okay, so am I missing anything there? A little bit about pseudocode. Flowchart is a picture. Computers cannot work with the algorithm. So that's the thing, right? We got this algorithm, as the notes say, that's not enough for a computer. You can't give a computer a flowchart or pseudocode. You have to do something. You have to code it. So coding it is going to put it into a computer language. Now, somebody's going to tell me I'm wrong. We're going to have these, what we call these fourth generation, fifth generation language, which can take somebody's pseudocode and turn it into a program. All right, so that's a special code generator. There is a such thing. So, all right, so just that person in the class who's going to say, Mark told us a lie. Computers can take. It's not really very common, all right, but there are such things as code generators that will generate programs from things like that. So a computer program is going to be as it says, it's a formal language. So we know languages, like I only know one, sorry. I can understand a few words in a few other languages, you know, a few words in Arabic, a few words in Tagalog, I got that, a few words in Spanish, because I know that, a bit of French, which I was supposed to learn when I was in high school, you know, a little bit of German. Okay, so few words, like we're like that, right? Some people can understand a lot of words, and like you can. Most of you can understand 2 languages at least. So programming languages are like that. Maybe you could understand C. Maybe you could understand Pascal, and they're kind of similar. Maybe you could understand Python, etc. So it's like a language. It has its own special words and things. It's like a language, but most of it's based on English, most of them. Okay, so yeah, we use a special word there, strings. A string just is like a word or a bunch of words. And we find those put together in a special way. That's how programs work. Anything else I need to say? All right, yeah, okay, so here it's talking about CPUs with their own instruction sets. If you're talking about first generation languages, remember I said their first generation languages is just machine code. And even second generation languages, which is your assembler language, those languages would be specific to a particular processor. So that means if you're running something on an IBM computer, it would be a different program than if you were running something on a Bull, on an Apple, whatever. They would have a different processor. The program that you wrote here at your first generation, your machine code, would not work here. Now, actually, when we write programs, we're writing them at this third, which is high level language or higher. And we have something in between us and the hardware, which is an operating system. And our compiler is able to work with that particular operating system. So for example, you might have noticed this when you might download something as an app to run on your computer. And you have to download the right one, right? If you're using an Apple computer, Apple phone, you need to download from the Apple store. The thing that's on the Android store won't work on your Apple computer. Sorry, your Apple mobile phone, because your Apple mobile phone has a different processor. It won't work. Now, the person who wrote that program, that app, might have written one app and made it work for both Apple and Android by compiling it differently. But the actual compiled code that's going to come out is different. Okay, so one would be compiled for Apple and one would be compiled for Android. They're different because they have different processors. Does that make sense? You know that. You've come across that. So when we talk about machine code, that's the kind of code that you take your programming language and you convert it. The actual process we call is it's either interpreting or it's compiling. And you have to convert, because computers can only understand machine language. They only understand zeros and ones. They don't understand all this other stuff that we're talking when we're writing our Python program. We have to convert it. And we use that converting, we use the word, we say compiling or interpreting. All right, so yeah, enough on that. And there's lots of videos there that are associated with that you can look. Now, here's some yeah, there's a bit there about interpreted programs. I can mention that in a minute. The idea here is supposed to be doing the same thing in different computer languages. All right, so here we got a bunch of code that if you were doing machine code, and notice that everything is just zeros and ones. That's machine code, because that's all the machine does. All it knows is zeros and ones. Even the locations are 0 1s. Everything you see there is zeros and ones. That's machine code. All right, and then this is in binary, as you mentioned, binary. We could convert it into hexadecimal. It's still zeros and ones. Well, no, we've got some 7s and Fs and everything like that. But actually, hexadecimal is just based on binary. You will see then when we do our tutorial this week, we're going to be playing around doing hexadecimal and binary. And you'll see where we get this Fs and Es and that kind of stuff from. You'll see that all we've done is we've converted the zeros and ones into something that takes up less space. That's all it is, right? It's just taking up less space. But so that's our lower level language. Then if we go to the second level, our assembly type language, what we actually have is we have some special little commands, right? Look at those little commands. This is what it means, all right? But LDA 04, right? So what it's saying is in this location, load this value, and then add to this value. All right. So the commands are, they're what's the words that we would use? They're cryptic. They're arcane. I mean, you'd have to sit and study how to do assembler language to get this right, right? And then you have to think of every little thing that the computer's going to do, right? You're going to have to say, in that memory position, put this, and then in that memory position, put this. That's way too much work. And so we have operating systems to help us do that. But that's what your assembly language program. These things are just comments as well. And there's some of the special commands that you can use. Now, if we went to the third level languages, we get something like this. C. In C programming, what we'd say is, okay, create a variable called this. I'm translating this into English, but what this means, int a equals 83. What that means is create a memory variable called a, which is of type integer, and make its value 83. Create an integer variable called b, and make its value minus 23, and create an integer variable c, but don't put anything in it. So it'll have a null value. So that's what that line of code does. It actually does quite a bit, right? And then we got another statement which says add the two together and put the value there. Now the same program in Python kind of looks similar to the C, but it's a little bit simpler because we don't have to specifically say what type of variable we've got. We don't have to say that it's an integer. Python lets you sort of do that. It sort of implies it, right? The fact that we made a take on the value of 83, well, that's 83 is an integer, so a must be an integer variable. It's just like that. So Python's a little bit more flexible with the variable typing. So we say that, yeah, it's a nice programming language to use. It can do a lot of things. Python does use an interpreter. We talk about here this idea of an interpreter. With an interpreter, what we do is we take each line of code, one line of code at a time. We do the decoding and the processing before we go on to the next line of code. And so it's a little bit slower, but it means that you're seeing those lines of code as you go and you can interfere with it. With a compiler, it's a little bit different. With a compiler, what we do is we take the entire program and we convert it into machine code. And so all we've got is a bunch of zeros and ones. And then that is saved as it's compressed and saved as a file. And then that file is distributed and we run that. And that file actually sort of communicates directly with the processor because it's zeros and ones, right? Now, that's how we typically distribute sort of professional built code. And the reason we do that is because we're not distributing the code. All we're distributing is the compiled code, and compiled code is very hard to decompile. So it's hard for somebody else to see what you did. So it's hard for them to steal bits of your code. And so, for example, you try and have a look at the programs that are distributed with a Microsoft operating system. You could see the zeros and ones. You could open up an exe file or a DLL file and look at it, and you could see it in hex, or you could see it in binary, but you wouldn't know what it means. I mean, you know, it's just, but it does do, what it is it's instructions to the computer. All right, so here, I don't know if I want to spend too much time on this. The low-level programming languages, I already mentioned this. If you're talking about level 1 and level 2 programming languages, they are device specific. They're specific to a particular processor. All right, so as I was saying, the one that you made for your Apple machine is not going to work on your Android machine. Your Apple Mac computer program is not going to work on your IBM compatible computer, and that's because it is calling specific resources in the machine code, and it's machine code that you kind of got. And how are we doing here? Are we just about done? Yeah, high-level languages. So I've already mentioned a few high-level languages: C, Java, Python, Fortran, COBOL, all of these high-level languages. What we do is there is something that we can read. It's quite easy for us to read. We either distribute it as an interpreter, or we compile it. More likely, we compile it. Compiling takes a few steps, but the result is just a bunch of zeros and ones that can be used. So that's what it refers to here under compiled, and that's typically how we do it. And I think that might be it. Okay, so yeah, I think that is it. So last slide there, is it? Is it the last slide? There's a bunch of computer program types. JavaScript. JavaScript is, if you guys are doing the software strand, you will be learning how to do JavaScript. So JavaScript is a programming language which allows you to have dynamic web pages. What I mean by dynamic web pages is that you can produce buttons and things all over the page, where when the user touches them, the web page changes. Not just that you go and load a new web page, the web page changes. So that's JavaScript. It's kind of powering what we call Web 3.0 or 2.0, wherever we are now, 3.0, I think. PHP is kind of like that, but PHP allows you to work with a server that will work with a database. So for example, SQL server. So PHP will allow you to make commands to retrieve and to write things onto a database server. That would be important if you're running a business, right? Because you'd want to have a record of all your customers and all of your items. You'd need a server to do that. So PHP is going to be very important with that. Java. So you may have heard of the Java programming language, right? So Java. What's cool about Java, and Python's the same, is that it's a object-oriented language. So with object-oriented language, we have objects, and objects can have attributes. They can have classes. They can have methods that go with them. Though that might not mean anything to you now, at one point it will mean a lot to you. All right, when you start writing programs with objects in them. It's the more modern way of programming, and it gives you a lot more flexibility. Python is also object-oriented. Python is, I think, more modern than Java. A lot of universities and colleges used to have their introductory programming language would be Java, and a lot of them have swapped over to Python, and some are not even doing Java anymore. All right, so Python, it's easier to get started with Python, and you can do just about everything that you could do in Java. The real key to that is the libraries that come along with it. So you'll learn about that as you do your programming. I mean, I know I'm just saying the word library. What's that? Basically, libraries are where other people have written programs, that do special things, and they've proven those programs to work. And then that program is distributed as a library with a bunch of other programs. And so we can just use somebody's already written a bunch of general purpose programs that'll do stuff for us. So you'll find that you'll have libraries that are written in Python or for Python that will do many things that you'll find at a very sort of technical sort of engineering level. So there's Python libraries that allow you to make changes to the operating system. There's Python libraries that allow you to control routers and switches. So, you know, whether you're a computer technician type person or whether you're a software developer, you'll find that Python will be quite useful to you, and JavaScript. Now, Ruby on Rails and R, I'm not really so familiar with. C++, it's kind of like Java and Python. It's an object-oriented programming language based on C. So it's probably a little harder to write programs in, because I think Python's a bit easier. Ruby on Rails and R, as far as I know, they're sort of associated with big data and artificial intelligence. So that's, some of you will be doing big data and artificial intelligence, so you'll probably work with those. And there's some notes about all of that. And I think I'm finished. So I'm going to take any questions that you guys might have. And any questions?